Hey, how you doing? Once again, this is Kyle, and I'm going to talk to you some about engineering economy, and just a few of the functions we use in engineering economy, economic functions that'll compute final worth, present worth, annual payments, and take from gradient and turn it into annual. Basically, what all that is if you have a final worth given to you, and that's after interest and stuff, and you want to know the upfront cost. You say, well, how much does it cost me to pay you right now? It's very helpful to know the present worth, just so you know actually how much will be going out of your pocket. If you think of $10,000 20 years down the road, that might sound like a lot. But if you find the present worth and you see it's only 4,000, it's just a lot of interest. And if you don't pay it off then, it's going to be 10,000. Then you say, well, I want to pay the 4,000 up front. Different things like that. It can go for making money, it can go for spending money, and losing money. So we're just going to go over a few different engineering economy problems, and we're going to use Postgres to actually display how they work. So first type is single payment. It's just a final and a present. You either pay all up front or you pay it all at the end. And decision-making analysis, whether paying all up front is an option or if you just want to compare in today's terms, at today's value, how much is this actually going to be worth. These are very handy formulas. So over on the Postgres side, we can go to finance or fin, and then in the scheme of finance, I have 7 different views. And our first one is going to be single final worth. With single final worth is taking a present worth and computing the final from it. So right here you see my SQL statement, and in order to calculate the final worth, my very last select statement, I took my present value, multiplied it by 1 plus the rate, and I put that to the power of n. N represents the number of times it's compounded, and obviously the rate is the rate at which it's compounded with respect to n. Whether n's a year or n's a month, the rate respects that. And then it outputs it as calculated future worth. So if we actually open up this table, view data, top 100 rows, you'll see that it outputs the calculated future worth of all of these, which is really neat. There's also a given value that each of these had a given amount to start with, and then the rate was compounded, and just it adds up to a new value. See all the decimals? It is because it's to a power. We're going to get more into that when we actually get to the equal payment. But then this also works for present worth when you're going the opposite way. You see, present worth is a similar formula. One of the big differences is you start with future value, and it's actually completely switched. It's the other side of the equation, which you can see from the left side when you see the actual equations and how they are written. And then when you open up present worth, there's the present worth, and you see right here the given future value, and it calculates the present value for us. So if we did have to pay, I believe that's 10 million. In present value terms, that's only 6,139,000 at an interest rate of 5% over a 10-year period. So depending on what your company can afford now, what you think your company will be able to afford, if you're going to make more money than the rate of interest in the next 10 years, you might want to wait, pay it off later. That's kind of what it tells you. Now we're going to get into a little bit more complicated. These are equal payment series. They have an A, which is annual or in terms amount, and it's the same amount every single period. So every n period length, you pay one amount, and it's consistent. So That's what the A represents. And these are very common just in our business society. If you go to look at a new car, they say, well, you only have to spend $240 a month. You can have this car for just $240 a month. And where they get you is over 40 months, most people don't know how to calculate, well, how much am I actually paying? They think 240 a month, that's only a fifth of my paycheck. I can afford that. But once you actually calculate how much you're paying, you might end up paying $40,000 for a car that's only valued at $25,000. So that's when these formulas come in handy. We will look at present value from amount. So you go to a store, they tell you however much. The equation you see is the last select statement, and it's also over on the left here. But so it's a very long equation, and it's just taking the things I've already entered, and it's going to output our future value as you see there. So when we view the table, you can see the initial amount was 150, paid for 60 months or 60 years. Whatever it is, the rate again reflects that. So if it was 60 years at a rate of 1, and you wanted to make it into just months, you would divide the rate by 12. And it's going to be a little bit higher, but that's how you would do it. And so $150 every single month for 60 months results in $6,743 if you were to just pay it all at the very end after interest. 4,000 becomes almost 200,000, and 20,000 at a 0.5% interest rate becomes over $1 million. Future value from AMT, it's very similar to present value. It's just instead of doing the future value, they add in like the equation we did for single. That just kind of switches the two to figure out what present value is. You see the equation there. View data, top 100 rows. In this equation, I put in the same exact 3 that we just saw for the present value. Excuse me, the last one was present value, not future. This is what we see for the present value, and this is the future value, and you see the numbers are higher. Like the other one was just over $1 million. Now this is at 140 million. So a future value is going to be more expensive because it's after interest. Present value is up front, so it's going to be cheaper. Now this is amount from present value. Now these are 3 different ones, and what it's taking is you give it a present value. Someone says, car costs $24,000. You can just pay it to me over 30 months, and we'll do a rate of 5% interest per month. So you'd be looking at $1,561 every single month. And although it seems like you'd be spending less than $1,000 because it's 30 months, the interest adds up and you end up spending a lot more. You can see very similar results with the other 2 as well. And then amount from future value. You give a future value and it'll tell you the amount and with the respective rate. So if someone says, I'll do a job for you, I don't need the money up front, but in 60 months time I need to have $47,000. Well, then you want to know, well, how much should I put aside each month so that I can pay him that money, or how much should I put in the bank and make 3% interest on? And you want to put $288 a month. So that's kind of how that works. Now, there's also Uniform G down here, which is a uniform gradient series. Now, this is if someone says, I want to increase the payment by the single factor every single month, every single period. So for the first period, you add $100. Next period, you would add 200 from the initial, or 100 from the previous. In third period, you add 100 from the previous, 300 from the initial. And it continuously adds in a ladder form. So at the very end, you could be paying $20,000 in 1 month. In the very beginning, you only had to pay 100. This might be useful if you see down the road you believe you're going to get a job, but right now you don't have the money. Start paying lower, and then as you start making more money, you're able to afford the higher payments until it's completely paid off. Or just different scenarios. That's a way to look at it. So the equation for this can be found right here. And when you actually type it out, it's a very long equation. But I put that as my last select statement, the equation we want to find. Now, if we view the table, top 100 rows, this gives us the 4 because I only put in 4. And it's an A over G series. Find the amount given the uniform gradient. And you see I listed the first one for a car, uniform gradient at 1,000. Now, what this does is I put in 24 months and it's only 0.5% interest. So if you're paying 1,000 the first month, and it adds up quickly, and notice. Second month you're paying 2,000. Third month 3. By the 10th month you're paying $10,000, and by the 24th month you just pay 24,000, and that's a ton of money. And so you're looking at like a crazy Bugatti here or a McLaren. Super expensive car, but this just shows how quickly, because 1,000 does not seem like a lot, but when it's using the uniform gradient series, starting at 1,000 over a 24-month period is equivalent to, you see under the amount column, paying $11,260 every single month for 24 months. And then if you were to run a future value on that at the same percentage rate, you're looking at 11,261 times, you could be looking at 26, more than the 24. And you see the other ones also very similar. You're paying 11,250 first month, then 22,500 the second month. It adds up. You'd be equivalent to spending 138,500 every single month for the next 30 months. So these are just to show how quick the gradient adds up. These can be done on a smaller scale, but this is very useful formula useful to know when you do have a situation that involves a gradient that's an increasing cost or an increasing revenue, or however you want to look at it. This can be used, this formula. Now, if we just discuss probability sum, we can go to lot down here. Now, these are lottery numbers. I'll open up my lot table. You see all the columns I have. We go to view data, view top 100 rows. Now, if we want to analyze this data and say, well, how many possibilities really are there? Because I want to win the lottery. And what's the odds of winning the lottery? What you would have to do is first decide whether there's a permutation or combination. Permutations, order matters. So, like for instance, in the pick 4, you want to pick 4 in the correct order, numbers from 0 to 9. And if they're not in the correct order, you don't win. But for this lottery, this is the Mega Millions, all you need is the correct numbers. They do not have to be in the right order, except for the very last number, which is only 1. So it doesn't affect the permutation formula at all. So this would be a combination, because order does not matter. If order did matter, like in the pick 4, then you would use a permutation. A permutation has a lot more possibilities, and the odds of winning are a lot less, because order matters. So each opportunity then can be entered in every row and switched. So combinations, there's a lot better chance of actually winning